So let me start my lecture here. So first we are going to use LT Spice. So I will search for the simulator. There are recent versions are available over here, but I am using the this version of LT Spice, very old version. Uh, uh, the support for this actually they have stopped supporting the update version for this one. If I use this one, some of the GUIs I'm not comfortable. So still I'm working with the previous version, whatever I worked on. If you download it, it will take some time for you to some updated libraries are getting added over there. So minimum 15 minutes it will take for you to download, install, and it will take some time. So finally, I have installed the tool. The tool is available here. Okay. First, before letting into the steps, whatever I have to do on, why we have to go for simulation based softwares? What is the need for simulation softwares? What is the other way? If the simulation softwares are not there, what will you do? You have to directly buy the components. You have to make a PCB board as a prototype. You have to verify what is the voltage you expected, what is the current you expected. If these things are met, then you will go for the device. I mean, final product. Correct. No? That is one of the reason why we are going for SPICE-based simulations. The other reason is that, for example, in my circuit, I have, for example, the transistor what you might have used in your I mean amplitude modulation analog lab, communication lab. You have used it on using BC547 transistors. Yes or no? Common emitter, common source. Yes or no? You have done that type of lab. There you have used physical transistor, bipolar junction transistors for doing the experiment. But the problem with that circuit and this circuit is that they are large scale devices. We are in VLSI, we are talking about nanoscale transistors. Nanoscale na 1 into 10 power minus 9 is a dimension of the length of the transistors. Correct? Na? That you cannot even feel in your normal eyes. Are you able to follow me or not? See, our thickness of our hair is micrometers. Lesser than that is nanometer. So you cannot just like that see in your neck. Then how will you connect wires and capacitors to that particular transistor? Not possible. Physically, you cannot take a transistor in hand. You cannot connect it in a physically it is not possible in a PCB board also. So what is the only option is that you have to fabricate it. So fabric PCB also somewhere around 1,000, 2,000 if you spend that money can be recovered. The cost is about around 2,000 only. But if you say go for fabrication, the cost is some lakh that range. The even simple circuit also will cost around lakhs because you have to set up the foundry, you have to fabricate for that particular circuit, then you have to make the things correct. So the cost is very high. But moreover, if you do that all fabrication also, there is no guarantee that it will work properly or not. Correct or not? So that is why we are going for simulations. If everything is working perfectly, then only I can go for fabrication. That is why we are going for simulation-based softwares. And one such a simulation software is SPICE, completely open source software. Some of the IC libraries are also available in this LT space. The resource person is Analog Devices. Actually, the company is Analog Devices. They are providing and free sources for simulation. That is what linear technology. LT stands for linear technology. SPICE. Fine. I will go to the tool from now on. First, let me say what are the experiments we are supposed to do now. We are supposed to do 3 main experiments. DC analysis of NMOS and PMOS. DC analysis now it includes both input characteristics and output characteristics. Okay. Now the next one is about VTC curve of CMOS inverter. VTC curve of CMOS inverter. The next one is transient analysis of inverter. If interested, you can try for NAND gate, NOR gate, or any other logic gates or any other functions you want to try on. But I will try to give a demo on CMOS inverter. Okay. So this is the plan for today. I will try to give the demo on how to do things for all the 3 experiments today itself. Okay. Now first, assuming you have installed the software, and I will open the software directly. Fine. Now first step is that I will click the button over here. It is creating a new schematic. The work area is available for us right now. And I hope you are able to see at R gate shaped symbol is there. Okay, if you click over there, components library is available over here. So I will now click the NMOS transistor. You see this here, this is a symbol of a NMOS transistor, and I hope you are able to see the blue color over here. Correct, Anna? And here it is a 3-terminal NMOS. NMOS 4, it represents a 4-terminal NMOS. Am I clear or not? I will select the 4-terminal NMOS. I am placing it over there. And see, if I just select the component, it will be keep on coming. A number of times I click a number of components, it will be iterating. Okay. So in order to remove from this option, you have to press escape over here. If I press escape, that I cannot place furthermore gates over there. I will remove all the remaining gates, whichever want. I'm just going to do the DC analysis of NMOS. I'm going to do now. Okay. So now I have taken a NMOS transistor. I have to take some voltages. So I will again go to the components. I am taking the voltage source. I'm taking 2 voltage sources. First of all, you should understand what circuit I'm going to implement. So first I will take the blank page. The circuit what we are going to do now, in order to verify these 2 characteristics, I have my VGS versus ID drain current. The graph will be like this. And I have the other curve called VDS versus ID. The graph will be like this. This is for one value of VGS. And if you are changing the VGS other things, you will get this curve. So this is VGS 1, VGS 2, VGS 3, and VGS 4. I need these 2 graphs. Okay, this is what I'm going to this is called the input characteristics of my NMOS. This is called as output characteristics of NMOS. Already we discussed in our theory. But how to verify the input characteristics and the output characteristics for a given NMOS? What circuit I have to choose? First, I will take a NMOS transistor. I will assume the source. This is the source terminal. This is a drain terminal. I will connect a voltage source here. I will take more voltage source over here. Now, this will be connected to ground. Okay. Now, I will call this is a gate. The voltage between gate and source, I will call it as VGS. This is a voltage connected between drain and the source. I will call it as a VDS. And the current I am going to measure here. Okay. So in order to get this curve, what is a variable quantity here? VGS is a variable quantity. I have to measure the current. Correct. So what I will do now, I will make VDS is equivalent to 1 voltage. I will tune this voltage to 0 to 1 voltage. Like in RPS, you will change in a voltage. Tuning. Like that, I am going to tune the voltage at the gate to source voltage linearly in the range of 0 to 1 voltage. So which means that I am going to linearly increase the voltage from 0 to 1 voltage. Am I clear or not? That is what I am going to do now. And I am going to verify whether the current is following this pattern or not. Where I am observing the current, at the drain node, I am measuring the current of this particular circuit. So that is what I am going to do now. The same circuit, try to draw it over here. I have taken the component so far by pressing this button, and I have to take the ground also. I will take it over here. Now, see, for wiring, I use this pencil shaped symbol. For zoom in and zoom out, both are possible. For my in my system, you can just if I don't know how to say that. If you scroll the mouse, you can observe the zoom in and zoom out option. Okay. In order to connect it, please follow me here. I will pressing on the pencil button. I am not pressing any buttons in my mouse now. wherever I want to have the connection, I go there, the marker is moving there, click, and then move on to the next stage, and then once again you click over there. Am I clear or not? The connection is done. Now again the marker is there. For the gate voltage, I'm just moving the mouse. Till now I did not make any press on my mouse. I'm clicking at that particular point. I'm moving the mouse and I'm pressing on the next terminal wherever I want to connect on. The connection is done like in that manner. So press here, and I will have a common ground here. This is also connected to ground. This is also connected to ground. Now here I will connect it to supply voltage. I hope you can understand. Just move the marker, press here, don't do anything. Move to the next terminal wherever you want to connect it, go there and press the button. The connections are done. I have connected the component. This is a very simple circuit. One transistor, two voltage sources are connected, but I want to have my convenience. What is my convenience? Now here the voltage is named as V2 and V1. Okay, fine. Now I am going to make some adjustments over here. Please follow me. I want to name this as VGS. Go to the V2. You please see here. Go to the V2. Right click over the name. I will type here VGS. You can give V in also, V out also, whatever you want to give it. I can change it. And for C, here the voltage is now mentioned as V. So go to here. Again, right click. You can give the DC voltages 1 voltage. For giving value, go to the component, right click over there. A tab will open over there, and then you can change the name, value of that particular component. Similarly, here V1, I'm going to change it as VDS. And this voltage also, I'm going to give it as 1 voltage. So far, the connections are done. Correct, na? Now, fine. Okay, now let me just show you how to give the simulation command. In the top, you can see some button called the simulate option is there. Click over there. It is keep on flickering. Okay, I am going to the simulate option, edit simulation command. And here you have different options of simulations are there. Transient simulation, AC simulation, DC simulation, many things are there. Now I am going to do the DC simulation alone. So I am going to select the third tab. DC sweep option is there. I am selecting there. Am I going fast or is it fine for you? For all. And here first source, second source, third sources are there. I'm going to change only one source. VGS alone I'm going to change. So here name of the first source, what I'm going to choose now, VGS. I selected. This name I typed over here. That is the source I'm going to change. X-axis is VGS is changing, na? And I'm going to change it in a linear way, 0 to 1 voltage. So start value is 0. Stop value is 1 voltage. Increment of 0, 0 0.1, 0 0.2, how many, in what step you are going to increment now? I am going to increment for 0.1, 0.2, like that, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1 voltage. Like that, I'm going to increment the 1 voltage. So this is a step value. Now your command for DC simulation has started. Am I clear so far? What I did, I take the components, I did the wiring, I changed the name of the voltage sources, whatever I want to change on. I go to simulate, edit simulation command. In that I selected DC simulation. I just selected VGS is the variable, 0 to 1 voltage is the increment of 0.1. I changed that. Aarthi early again. You Dinesh refer na board. So that is what we are going to do now. Okay, let me just try to run the simulation. I will moreover select the window, tilt vertically. Okay. I will go here. There is some option for run. Okay. I will click here. Like a run symbol is there, na? I will select here. This option I'm talking about. I will click over here. I will go for window. Okay. Now a plain window is available over there. You see, if you move the marker, somewhere it is showing like red color pin. Correct, na? Like knob it is showing on that will measure only the voltage. But if you move the marker somewhere, it will like a black color terminal it is showing. That is for measuring current. Okay. If you go here, this is what the drain terminal for my transistor. And if I click over there, I can get the curve. I can get the curve. I hope you agree. You are able to see the x-axis is the voltage, y-axis is the current. You see, microamperes is the units are. The voltage is in increment of 0.1, 0.2 till 1 voltage. The voltages keep on increasing. Okay, if not visible, I will try to just plot the waveform alone. I am able to show you now. Am I clear so far? Yes or no? Okay. So far, what are the doubts arised for you? One fundamental question you should have asked me. What is that question? The curve, whatever I said, I plotted it here. What is the curve I asked? I said I will plot. Na? I said I will plot this curve. I plotted this curve. I did my job. Correct, na? But what is the question you should ask me to ask me now? What technology of transistor I'm using on? Whether it is 45 nanometer, 90 nanometer, 1 micrometer, what is the actual technology of that particular transistor? Correct, na? There are many technologies available. What technology you are using? That is what you should ask now. Are you able to follow me or not? How can I do that, na? Go here, go to browser, minimize things. Okay, use just a type P. Okay, predictive technology, PTM model file. Okay, I'm just selecting PTM model file. PTM stands for predictive technology model. Okay, I'm just clicking on the first link. Use make a note. PTM model file, predictive technology model file is provided by this university. I'm clicking on the first link. It is leading to different types of transistors are there. FinFET models. FinFET is another type of transistors. Advanced version of MOSFETs is what FinFET. The bulk CMOS transistors are there. And here you can see that high performance, low power applications. You can select this type of transistors: 22 nanometer technology, 32 nanometer technology, 45 nanometer technology, 65 nanometer, like that. Many such models are available over there. Okay. Now I have chosen here 90 nanometer technology. You can choose any one, but I have already chosen the 90 nanometer technology. I'm just clicking over here. The model file of that particular transistors are available over here. Okay, 90 nanometer NMOS, dot model NMOS. There are many parameters over there. From here to here, everything is for NMOS transistor. Might be 150 parameters might be there, or more than that also will be there. Okay, so what I did now, from here to this line, I copy pasted as NMOS. Where I as a notepad file I selected. You see here already I made the things over there. NMOS. You see already I open a notepad file. From there to last line before PTM of PMOS is there. I copied from that file. I pasted it in a notepad and saved it as a NMOS.txt. Text file, just a notepad file, I saved it. Similarly, from the next line, which means from this line to the next level, I copy pasted and made it as a separate notepad file called as a PMOS transistor. All the parameters are available over here now. I made a 2 notepad file. I saved it as NMOS and PMOS. That's it I did. Dot text file only, not any other C file, C++ file and all not there. Just a model file. The data file I saved it on. Are you able to follow me, sir? What are these things now? In theory, we should have studied no. Parasitic capacitance are there at many nodes. What is the threshold voltage of that particular transistor? All these things are defined over there. We have discussing only few parameters in our theory, but there are nearly 200 parameters might be there for a single transistor. But in order to do the simulation, such a way that it is working like a real-time transistor, you have to consider all these parameters. Are able to follow me or not? Then only it is very good simulation tool to, if the model file is not considered, it is a generic transistor what you are doing on. If you do the give it for fabrication, it will not work for 45 nanometer or 90 nanometer if these model files are not included in your simulations. Are you able to follow me or not? Actually, these parameters should be given by the foundry person. For example, Samsung, they are making one transistor. Now they will give these model files. After fabrication, they will measure what are the parameters. Then they only can give these model files. Okay. But this university has provided us the technology model file for free of cost for our educational purposes. We are using it for our simulation. Am I clear or not? So unless until you are including this model file in your simulation, it is not a 90 nanometer technology. It is a very generic type of simulation. It is not considering what is the size of the transistor, what is the threshold voltage. Nothing it is bothered about. Just a very default size of the transistor, very default model file it is going to work on. Am I clear or not? So how can I include? See, I have downloaded it to notepad file, but how does the software know that these transistors are meant for this model file? See, in the simulation, I have something called that NMOS transistor I have selected. Where is the marker? You see, I will close this tab. Okay. Now, I have a NMOS transistor, but this NMOS transistor is not accepting all those parameters for correct. Na? There are nearly 200 parameters are there, but those parameters are not so far included in this particular simulation file. Yes or no? How I can link this transistor symbol with those parameters? How the software is going to take all those parameters for my simulation? That is what we are going to do now. First, what I will do now, I will save this particular circuit, demo 1 of input characteristics of NMOS. Okay, some name I'm giving for saving the file. Then, in order to include that NMOS, because I have included only NMOS transistor in my circuit, I hope you are able to see the last option called spice directive.op. Correct? Na? I will click over there. Here you have to type dot include NMOS dot txt. Dot include also you can type. I'm just writing what name I gave for the file name. I will just 1 minute. I don't know what is the name, NMOS.txt only. So I will click here, do it once again. In the spice directive, I will write just dot without space include dot include space NMOS dot txt, not st, txt. Click OK. Dot include NMOS dot text. Click OK na. This command will come over here. But till now, it has not included anything in your simulation file. Okay, well, now what you have to do now, go to this command, move the pointer, right click over there, right click or left click, right click over there, right left, okay, dot include. Sorry, I made a mistake here. INCLU. Okay. After right clicking over there, you can, a new tab is getting opening over there. I will have option called browse. Correct? In the tab, new tab, I have option for browsing. After browsing it, you select that notepad file, whatever you saved here, and click open. And then click OK. Now you see here, the command was changed to that directory file, whatever you have included, .li, that directory of my file where I have saved C users, ASUS, desktop, spice, nmos.txt. Wherever you are saving that notepad file, that directory is now included over there. Are able to follow me or not? Till now, I have just linked our work area with the notepad file, but the transistor doesn't know what are the parameters you have to consider. Correct? So how can I do that now? First, I will make some changes to the notepad file. You see here, click open. What I did now, please follow me. I will do it once again. Go to this command, right click over there, click open. This is the model parameters, whatever you opened in a text file or notepad file, that is now opened through LT Spice. Are you able to follow me or not? Now you can see that I made one change here. Dot model NMOS is actually in the, you see, I will go to the website. Here you see dot model NMOS is only there. Correct? But since it is a 90 nanometer technology, I just changed it as NMOS_90. I just included dot model NMOS_90. I just, for some my convenience only, I added. Instead of NMOS, I can type my name, your name, whatever name, which is, it is a name for that particular model file. Dot model Marana, the name of that model file is Maran. Now, since it is an NMOS 90 nanometer technology, I renamed the name as dot model NMOS_90. That is for my convenience. If you don't want to change also, no problem. Okay. So for now, I just changed the name here and saved the file. Go to the circuit once again. You can close it. This is not a problem now. Okay. Now, if you don't want to change also, it will work, no problem at all. But what I am trying to insist now here, already I will do it once again. Go to the transistor, right click over to the mouse, right click over on the transistor. You have an option for model name. Now I will type NMOS_90. Are able to follow me or not? What dot model, whatever name you are giving for in that file, that name should be called here for name of the model. Are able to follow me or not? Then only that note, whatever parameters available in the nmos.txt are included in this particular transistor. Am I clear here so far? First, I downloaded the notepad model file. I included in my work area. Then that library file is included to the transistor now. I am right clicking on the transistor. In the model name, I am typing whatever name I typed in that notepad file. NMOS_90. Now I am typing it as a NMOS_90. Are you able to follow me or not? Now, the length of the transistor, I will select it as 100 nanometer. Width of the transistor is also 100 nanometer. W/L ratios are same for this transistor. If you want to change here as 200 nanometer or 400 nanometer, you can change it on. I'm just clicking on OK. You see now what are the things I changed? If you want to verify, go to the transistor, right click over there, model name, length of the transistor, width of the transistor, 100 nanometer, and for length and width I have given. You should have asked one more question also, sir. Can I give 10 nanometer for length and width? Can you give it over here? Can I give 10 nanometer for both length and width? Here in the example or demo, whatever I shown here is length of the transistor is a 100 nanometer. You can use 90 nanometer also, but can I give lesser than that? No, because you know that the model file what you downloaded is 90 nanometer technology. 90 nanometer now, not about dimension of the transistor. Length, the W/L ratio is what? Length of the transistor is what the technology what you are talking about. Correct, na? Spacing between source and drain is the length of the transistor. That length is equivalent to 90 nanometer. So lesser than that, definitely you should not give for any transistor if your model file is 90 nanometer. Are able to follow me or not? If the length is 90 definitely width can also be not lesser than 90 nanometer. Are able to, for safer side, I have given length equivalent to 90, 100 nanometer and width is equivalent to 100 nanometer. You can give the change the width of the transistor, but not the length of the transistor. Am I clear or not? Don't change the length of the transistor, change the width of the transistor for your convenience. For a technology, if you are using 90 nanometer technology, for all the transistors in that technology will have the same length. A designer can have the flexibility of only changing the width of the transistor, not the length of the transistor, because that is predefined in that particular technology. You cannot change the length of the transistors. Am I clear or not? So now I have defined the width and length model file are included for this particular transistor. I saved the particular design file. I am going to click on the run command. I will just click on window vertically. Now I am going to measure the same plot. I am moving the marker. I'm getting a current based symbol, clicking on to the drain current. Now you can see that the curve has been shifted somewhere over here. Same type of graph only, but I assume that the graph is somewhat here like this. It is not touching till some 0.3 or 0.4. Previously, a slight variations was there for the previous plot when comparing to this particular plot. Sir, I want to verify whether it is this circuit is really taking the parameters over there or not. Are you able to follow me or not? How do you verify that? What is my question? You want to really understand whether this transistor is taking whatever is there listed in the model file or not. How do you verify that? You know only one parameter. What is that parameter? Threshold voltage. Correct? So in this diagram, where is the threshold voltage? Where my marker is there, somewhere around there only threshold voltage. Correct? If the VGS is lesser than the threshold voltage, transistor is in cutoff region. So here the current value is 0. Lesser than 0.3 current value is almost 0. Greater than 0.3 I have current flowing over there. Cutoff region and active region is available over there. Correct? So you know only one thing. Let us try with that particular option now. So what I will do now to verify whether my thing is working properly or not. Again, I will open the what I'm doing now, going to the command file where my model file is included .lib is there. No, I will go there, right click. I am clicking on open. That notepad file will open now. You see now I have one parameter called VTH0. There are many parameters are there. I don't know about all the parameters. I know only about threshold voltage. So instead of giving 0.397, I will give it as 69. I will give around 0.7 voltage. The threshold voltage I am giving it on now. Are you able to follow me or not? Now I will try to. This is not mandated for us. Okay. Now you please observe whenever I run the button, you just verify this portion, how this is shifting from this range to 0.69. Are you able to follow me or not? What are the changes I made there? I changed the VTH not equivalent to, instead of 0.397, I made it as 0.697. Okay. So instead of threshold voltage here, it should shift somewhere over here. Whether I don't know whether it will work or not. I will save this and I'm going to run the simulation. Have you checked that? The curve has been shifted from around 0.3 to 0.69. Somewhere here only the current starts to flow on. Until that it is almost 0. Correct? Now what are the changes I made? I made changes to the notepad file, but it is reflecting in the circuit simulation. Correct or not? So what it is trying to show you, the software is considering all the parameters. Correct? It is working for now 90 nanometer technology. Correct or not? That is what I am trying to prove it to you. Yes or no? Am I clear for all? Just one simple circuit. Any doubts so far? Because next circuit and all, I have already saved the file. I will just open it and I will let you know what are the changes you can make. Am I clear or not? First circuit completely clear? Okay, I will make changes to the notepad file once again, otherwise for all the circuits will be impacted. So I will change the model file as threshold voltage as 397. Okay. I will close this one also. Okay, now all things are done. Now what we have studied in this particular portion only we have studied. I will show what are the things we have completed so far. Now we have studied for NMOS input characteristics we have completed. Now I will show you what is output characteristics of NMOS. Am I clear or not? Okay. I will go directly to the already designed circuit. Click open DC NMOS. I have already done the simulations. Okay. Same circuit. Circuit is not changing. Are you able to follow me or not? See, in order to get this graph, in this circuit, I only changed the VGS. Correct, na? I only changed the VGS. I got this particular graph. But in order to get this graph, what are the changes you have to make to the circuit now? You see the graph properly and let me know. What are the variables I have to change in order to absorb the current? X-axis is changing. VDS I have to change it. Correct? And I have to change the VGS also. Two things I have to change. Correct? Na? So now I will do that portion alone for you. Same circuit, I will delete that portion alone. Go to simulate, edit simulation command. If I delete only, you will understand properly. Okay, I will start from scratch. Other things are same. Do you follow me or not? Other things are same. Just I have to change the simulation command alone. Go to simulate, edit simulation command, and I am going to do only DC simulation now. Go to the third tab, DC sweep. There you have two options are there. First source and second sources are there. First source, I am going to change the VDS. X-axis I am changing now. What type of sweep? Now linear sweep I am going to change 0 to 1 voltage in step size of 0.1 I am going to do now. 0 to 1 voltage in step size of 0.1 I am going to change the voltage. Please follow me here. Now I have changed only the VDS. I did not change the VGS. Do you follow me or not? VGS is constant 1 voltage. You see this gate voltage, whatever I have connected is 1 voltage. Are you able to follow me or not? So this is not the variable quantity, only this is the variable quantity. Are you able to follow me or not? Now if you run the simulation, where I have to absorb, drain current is where I have to absorb the current of my transistor. If you click over there, I am getting the DC output characteristics of my NMOS I am getting. Sir, you said you will plot this particular graph. This is what I plotted so far. But you are showing multiple lines, but here you are showing only one. This is drain current, this is VDS. Correct? Na? So this is what the graph you are getting here. You see here, it is linearly increasing the linear region. About that, it is approaching to the saturation region. Yes or no? But sir, multiple lines you are showing only one line. Why? This is for fixed value of VGS. VGS is equal to only 1 voltage I have fixed. You did not change the VGS now. Correct? Na? You see, here I have different value of VGS. VGS1, VGS2, VGS3. So I have to change both VDS and also VGS in order to get this type of graph. Correct? So what I have to do now, go to the tool. Again, right click over there. The DC shape, first source alone you changed. VDS is changing from 0 to 1 voltage. Go to the second source, type VGS. Again, I'm going to change it linearly in the range of 0 to 1 voltage in step size of 0.2. I'm going to change it. You understand what I did? In the second source, in the DC sweep, second source, first source is VDS, second source is VGS. I am going to increase the voltage of VGS 0 to 1 voltage in steps as of 0.1 or 0.2. I am going to change on and click OK. I am saving the file. If I click on, I am getting multiple curve like this. For different value of VGS, I was able to get a different, as you increase the VGS, I was able to increase the increase in current, drain current is increasing. That is what I was able to observe over here. Was the graph visible for you all? Now, sir, I don't know which graph is for which VGS. How can I note that? Right click over there, view, I can insert the legend. You see here, the green color. Where is the green color? The first line, VGS. This is for VGS. The last one is for VGS is equivalent to 1 voltage. Maximum current goes for maximum value of VGS. As you gradually see red color 400 na, here somewhere around the current is going to flow on. So what is observation here? If you increase the VGS, drain current also increases. Are you able to follow me or not? If what value of VGS you are increasing, how that graph is going to increase linearly was observed over there. Clear or not? Yes or no? Shall I move on to the next one? Okay. I will close this one. I will. Okay. So now what are the things we have completed so far now? I have completed input characteristics of NMOS and output characteristics of NMOS. Both are completed. Now I have to do the same thing for input characteristics and output characteristics of PMOS. Okay. Now again I will go back and verify my DC PMOS input characteristics. Similar type of circuit, but for PMOS, everything is reverse. VGS na I should call it as VSG. VDS na I should call it as C. Correct. Everything in reverse I have to do. Instead of changing everything reverse, what I did now, I changed the voltage in reverse. Instead of providing 1 voltage, I made it as a minus 1 voltage. You see, the entire circuit is similar to the whatever circuit I made over there. But what are the other things I made changes now? I changed in the PMOS transistor. NMOS 4 I took now previously. What I am talking now? In the component palette, I selected previously NMOS. Now you have to select PMOS. PMOS 4 I selected. Okay, ma'am. The substrate is connected here. Everything, all the rest of the things are same. Instead of VSG, VST, I changed the polarity of the voltage. Instead of saying it as 1 voltage, I changed it as minor voltage in both the cases. Now again, I have to change the DC volt. VGS I have to change from, you see now, I will show here. In the DC sweeper, first source, VGS I am going to change because I am trying to plot the input characteristics now. Correct, na? I am going to change from 0 to minus 1 voltage in step size of 0.1. In step size of 0.1. Previously, we wrote 0 to 1 in step size of 0.1. I incremented. Now 0 to minus 1 in step size of 0.1. I am running the simulation here. I will show it like this. Let me try to plot the curve. The curve is like this. You see here now, the curve is inverted because the voltage is inverted. Correct, na? So the graph of the curve, you see what is there in the x-axis. I will try to show only the graph to you right now. The voltage is increasing from 0 to minus 1. It is going in the reverse order. So the graph is also will come in this order. Sir, I want to plot it in other way. How can I change the plotting type now? Yeah, I will try it. I have not tried it so far. I will try it now. The DC sweep 0 to 1. Instead of that, I will start from minus 1 to 0 in step size of 0.1. The graph is coming in this way. Are you able to show me? Here it is coming like this. I will try to show it in the tool. Say, I am trying to change the VGS For NMOS, the graph will go like this. Correct? Na? In this side, na, it is VSG or negative of VGS. Do you understand what I'm doing now? This side VGS, na? This side minus of VGS. Then, so if you plot the curve, it will come like this for PMOS transistor. What I did now, the voltage is from -1 to 0 in step size of 0.1 I did. So start value is -1, end value is 0. In increment of 0.1 I did. So -1 plus of 0.1, here I will have minus of 0.9, minus of 0.8 till 0 it will increment. So the graph will be like this, I will have over here. Yes, sir, Nova. Now I hope you are able to understand what I am trying to do with the tool. You understand? Now, what is this graph now? It has plotted only this quadrant of graph only is what plotted right now. This is what in our window right now. X-axis is VSG. -1 to 0 voltage I have incremented. Y-axis is the current. The current is going in this way. Are you able to correlate what I did so far? Yes or no? Okay. Now, I have plotted the input characteristics of PMOS. We have to do it for output characteristics of PMOS. We have to do one. So we have completed so far input characteristics of PMOS. I have to do it for output characteristics of PMOS. I will open that DC PMOS characteristics. Okay, now in the simulate edit simulation command, the circuit is same. Again, for PMOS, the circuit will not change. But instead of changing VGS alone, I have to change both VDS and VGS. Are you able to follow me? I have to change both VDS and VGS. I have to change on. So I will go to the simulation edit simulation command. In the first source, I am changing VDS. Please make a note. In the first source, I am changing the VDS. I am in the range of 0 to -1. Here also I will try to change it as -1 to 0 in step size of 0.1. For VGS, I will change from -1 to 0 in step size of 0.2. Okay. Then I will run the simulation. I will close the input curve. I am going to plot the output characteristics. The graph is like this. For output characteristics, the graph is like this. Again, my output characteristics are now plotted in this quadrant. I will show you what quadrant I have drawn. For this is the input characteristics of both NMOS and PMOS. Now for output characteristics of both NMOS and PMOS, for NMOS, you have observed the graph like this. For this is the VDS curve. This is for VGS1. This is for VGS2. This is for VGS3. I am measuring the drain current. For this is for NMOS. For PMOS, how the graph will look like? The graph will be like this. So we are observing again only this quadrant, which means that this is the VGS minus of VGS. Correct, na? I am changing from -1 to 0. Actually, the minus of VDS, sorry. This is minus of VDS. And this is for different value of minus of VGS1, VGS2, VGS3. Like that I'm plotting here. So now you see the graph, it will make sense now. This is this quadrant we are observing the graph. Whatever I have highlighted. For PMOS, I am observing this particular graph. What are the changes you have to note down? You see here this command. There I changed from 0 to 1 voltage. Both VDS and VGS. Here I am changing from -1 to 0. The steps is you can define. Sir, I want more number of different value of VGS. I will try to show it here. You see how many graphs I have plotted now. Just if you are increasing the step size for different value of eaches, you can be able to plot for different value of curve. Am I clear or not? So now we have done for input characteristics and output characteristics of NMOS and PMOS. Okay, I will close it off now. Am I clear for the first experiment? Input characteristics and output characteristics of both NMOS and PMOS. Am I clear or not? Now I will go for VTC curve of inverter, transient analysis of inverter. On the one whole, I will complete all the things. Is that fine? Is that fine? Okay, I will complete. I'll open the VTC of inverter. In the previous diagrams, I have taken only NMOS alone or PMOS alone. Now it is an inverter circuit. Previously, it is not a circuit. It is a DC characteristics of NMOS and PMOS. Now this is a CMOS inverter circuit diagram. Correct, na? Now I will show what theoretically what we are trying to do na. For a CMOS inverter, VTC curve na, I will have this graph. What should be the x-axis and y-axis? VTC curve of inverter means what is the x-axis, what is the y-axis? Tomorrow quiz is there. Huh? V in here, V out here. Okay. So this is where midpoint voltage what we studied. Okay, well, now which means that I am going to change the input voltage V in. I am going to absorb the V out here. Are you able to follow me or not? That is what I am going to do now. In the previous circuit diagrams, I have just included only NMOS file and PMOS file separately. But now I have to increase to both NMOS.txt, PMOS.txt I have included. Are you able to follow me or not? You see here, I have included PMOS underscore 90. I have defined the dimensions of the transistors. And for NMOS also, I have defined NMOS underscore 90. The dimensions of the transistors are included. Am I clear or not? Now, what are the things you have to do now? You have to take the component NMOS for PMOS for voltages, two things, connect to the circuit diagram properly. Then you have to define, include the library file .nmos.txt, .pmos.txt, include that notepad file here. I'm talking about this particular lines. These two lines I'm talking about. Correct, na? And then I have make sure that this model file is included in the transistor, na? The same name, whatever I gave in the dot model of NMOS underscore 90, PMOS underscore 90. Here for PMOS, I'm writing it as PMOS underscore 90. For NMOS, I am going to use it as NMOS underscore 90. The dimensions of the transistors are given. For length 100 nanometer for both the things, PMOS also, and NMOS both, I have given a length equivalent to 100 nanometers for both NMOS and PMOS. For width also, I have given both same. 200 nanometer for both NMOS and PMOS I have given. Now, after doing all the things, I have to define this variable as, you can type over here, give it as V in, give for this voltage, you can give it as V out, and value by default, I gave it as 1 voltage. Then what are the things I have to do? I have to do the DC sweep for this voltage. Input voltage should be changed from 0 to 1 voltage because x-axis is V in. I have to change it from 0 to 1 voltage. So what I will do now, simulate simulation command DC sweep. I'm going to change the V input voltage linearly in the range of 0 to 1 voltage in the step size of, I will now change it as 0.1 voltage. Okay. Just the this voltage I'm changing it as 0 to 1 voltage. I will save the file, do the simulation. I will do it like this. Now I am going to measure the voltage. So I don't go for this type of button because that tool is for measuring current. Now your job is not to measure the current. Your job is to measure the voltage. Correct, na? So where you have to measure the voltage, this is where I'm going to measure the voltage. You see the red color pointer is there. The output variable node is available over. Click, go there and click the voltage. So now I was able to get the VTC curve, the green color curve. I was able to get over there. But it is not a very smooth curve. Correct, na? Like a rugged surface, it is there. Sir, I want a very smooth curve, na? You can change here. In the step size, you make it as 0.01 voltage. Then you will have a very good smooth curve. You see? Like as we see in our textbook, y-axis is the output voltage, x-axis is the input voltage. I was able to see a very smooth VTC curve of my inverter. Clear for all? Yes, sir. No. Okay, sir. In a theory, we have studied that if I change the, I am talking about this particular slide. This is the final midpoint voltage calculation of my CMOS inverter. VDD minus of mod VTP plus square root of beta P by beta n by beta P times of VDD. Correct, na? Sir, if I change the width of the transistor, whether the curve will shift to left side or right side? Can anyone of you say if I change the width of my PMOS, what will happen to this midpoint voltage? Whether it will increase or decrease? You see, very simple question. If I change the width of the PMOS, let me assume that I'm going to increase the width of the PMOS, beta P is going to increase. Why? What is beta P? Mu1 Cox W by L. I already said that L is not going to change for any circuit, always 100 nanometer. If you are increasing the width directly, beta P is alone going to increase directly proportionally. Correct? No. So if you increase the width of the PMOS transistor, beta P is going to increase. Now you see here in this ratio, if beta P is increasing, what will happen to the entire component? Denominator portion is increasing now, this entire component will go down. Correct? If this entire component is going to go down, midpoint voltage will increase. If the denominator portion is decreasing, now this portion will keep on increasing. Correct or not? Yes or no? Now let me try to get that particular analysis. Am I clear with this one? Yes or no? I am going to verify that if the width of the PMOS is increasing, whether I will get the midpoint voltage will shift or not. So what I'm going to do now in the same circuit, VTC inverter, I saved it as a new file. I will do it here. Sorry. So this is a regular circuit right now. I'm going to adjust the width of the PMOS. I'm going to show you that if I increase the width of the PMOS, the curve is going to shift to the right side, which means that midpoint voltage is going to keep on increasing. Now to observe that what I'm going to do now, you see there the dimensions of the transistors are there. I'm just going to change the width of the PMOS alone. So I selected the PMOS, right click over there, where you have already defined 100 nanometer and 200 nanometer is the length and width of the transistor. Now here, if you are going to type it as a variable, you are going to change it to 200, 500, 700, like that you are going to change now. Here I will make it as a curly braces. I will type it in the notepad. What I'm going to do now, the width of the PMOS, I first typed open curly braces. I just made it as WP. Width of the PMOS, some name you can give X, Y, Z, not a mat. No, that is not a problem at all. WP and I'm closing the bracket. This has to be typed in the place of here. In the width of the transistor, I am typing as a variable within curly braces, which means that is a variable now. That is a variable now. Now I have to change that variable. I are able to follow many different values. I have to keep on changing. I have to check whether it is working fine or not. First step is that go to the transistor. Whichever parameter you want to change it, I changed it as width of the transistor here. I changed it as WP. Then follow me. Go here for a directory file, .op file. Click there. You just type dot step. Step. Click OK. That thing will come over here. Are you able to follow me or not? What I did, I just went to directory file .op. I typed a dot step. Okay, va? Then after placing it, go to that dot step, right click over there. You will have a new tab will come over there. Are you able to follow me or not? Now, what is the variable I'm going to change? In the transistor, I selected as WP. Correct, na? I will type the name of the parameter I'm going to change is WP. Let me name it as WP because I typed there capital WP. Here also I should use the same parameter over there. WP is the name I am going to change here. Linearly in the range of, I will change from 100 nanometer to, I will make it as small letter, 100 nanometer to 1000, let me change it to some 800 nanometer in step size of 100 nanometer. So what I'm going to do now, I'm going to increase the width from 100 nanometer, 200 nanometer, 300 nanometer till 800 nanometer. For every 100 increasing width of the PMOS transistor, what is the shift in my VTC curve I'm going to observe here. After giving all the things, click OK. I am going to run the simulation. You see here. Previously, I got only one graph. Now I got multiple graphs. Correct, na? How many graph I will get? For 100, 200, 300, 400, 500, 600, 700, 800. So totally 8 graphs I will have. All 8 graphs are available over there. Sir, how do I verify that the curve is shifting to the left side or right side? Go here. I will just point to the, or I will change the color. Where should I go on? Color preference. I will change the background to black. Okay. Was the graph visible now? No, right? Okay, some graphs are visible. The background is very poor. Okay, I will make everything. Okay, now here I will try to install legends. View step legends. The I hear both the things are varying. Okay, there is a problem here because here I defined both NMOS also as a variable, PMOS also a variable. Here one step parameter is running. So I will delete this particular command. I will just run the simulation here. And I will try to add the legends. You see now, green color is for 100 nanometer. The text, I don't know whether it is clear for you. I cannot increase the text also here. I will try to show it. You see here now, for green color 100 nanometer, the graph is first it is coming. Correct, na? Now, for the dark blue color, 800 nanometer, you see where that graph is coming. The dark blue color is coming at the last side, shifted to the right side. What do you mean by that? First 2.5 now it is shifted to now somewhere greater than 3 voltage, 3.3 voltage, something like that. So shifting to the right side now, midpoint voltage is increasing. As I increase the width of the PMOS, I can see that the midpoint voltage is increasing. Similar way, if you want to change the width of the NMOS, what are the changes you will make now? In the width of the NMOS, you have to type curly braces, width of NMOS or some variable you have to define it over there. And in this dot step parameter should be sweep 100 to 200 or 800 nanometer, whatever step you want to plot on. Just keep it, you will get the graph. This is a proof of concept. Whatever theory we have studied, we are able to verify using the simulation tool. By adjusting the width of the transistor, the midpoint voltage will shift to left side or right side, or that is being verified over here. Am I clear or not? You have to do both for width of that PMOS step, one graph. You have this type of graph you have to get it, and the next graph should be width of the NMOS also you have to change. You have to plot that one also. Am I clear or not? Fine. And last one. Any doubts so far? Shall I move on? Huh? No, another முடிச்சிடுறேன். See, so far we have completed the DC analysis, VTC curve of inverter. Now last transient analysis of inverter we are going to study. Am I clear or not? Transient analysis again. I am going to take the same circuit. I will open the transient analysis of inverter. Same circuit. I am not changing anything. But this is now going to be a square wave signal. This is going to be now square wave signal. I am going to give it over there. What I am going to do now, go to the component, right click over there. I will do it. Okay. I will do it once again. I will delete it. And I will take it once again for voltage source. Okay. Now, if you right click over there, you can just give 1 voltage or 2 voltage only. But how can you give a square wave input to this particular circuit now? In the last option, advanced is there. Click over the advanced, select on pulse type of signal. I mean, I'm going to give a square type of signal to that. Initial voltage, I will give it as 0 voltage. V on voltage is 1 voltage. And time delay, I don't want any delay. So let me give it as 0 nanoseconds. Rise time, let me give it as 0.01 nanoseconds. 0.01 nanosecond as fall time. On time na 5 nanoseconds. Period is 10 nanoseconds. Number of cycles, I'm going to give it as 20 cycles. I'm going to give. So what is the period of clock signal I have assumed here? Period of clock cycles, what I'm going to give on 10 nanoseconds. On time 5 nanoseconds, off time 5 nanoseconds. So that's what I have given there. On time 5 nanoseconds, total period I'm giving it as a 10 nanoseconds. Sir, I want to have a 30%, 70% duty signal. That also you can see it on. But now I have assumed a 50% duty cycle. That's why both on time, off time, 5 nanoseconds I have chosen here. If you click OK, that pulse type of command is available here. I can take it and place it over there. Okay. Now I have given the inputs. Previously, you have selected the dot edit simulation command. DC sweep you selected so far. Correct, na? But now I am not going to do the DC sweep. I am going to do the transient analysis. Transient na, with respect to time, how long you are going to run the simulations? 100 nanoseconds from 0 to 1 nanosecond, 0 to 100 nanoseconds with the step size of 1 nanosecond. I am going to do the transient simulations. Okay. If you run the simulation, I will close it here. Wait, right vertically. Okay, fine. You see here, if you move the marker and press the input, this is the input signal what I have plotted now. Perfect square wave input signal I am getting over there. You see here, from here to here, 5 nanoseconds on time, 5 nanoseconds off time. That is what I gave, no? Total period of the clock signal, what I pulse type signal is 10 nanoseconds, 5 nanoseconds of on time, 5 nanoseconds of off time. Now I have to observe the output signal. Correct, na? So if I try to plot it, here itself the plot can be added, but I will make a new plane. Add plot plane. So this area I'm going to plot the output. Again, I will try to show it this way. Now I selected this area and this node I'm going to plot the output. So I will move the marker, red color pointer is there. I will click on the circuit. I'm getting the output now. The blue color line. You see here, whenever input is high, output is low. Whenever the input is low, output is high. You see the voltage range, 1 voltage to 0 voltage, I'm able to observe here. That is what an inverter, no? Input 0, no output 1, input 1, no output 0. Now it is working properly. Yes or no? But here you have to observe one thing. You are able to see some, I don't know whether it is visible to you or not. Some small glitches are there. I don't know whether you are able to see that or not. Or I will try to change the background here. You see here, now the glitches, this is what I am talking it as glitches. A small line is available at there. At every transition, you are seeing some spike over there. Correct, na? I don't want to have that spike, na. You add a parasitic capacitance at the output node. Sorry, that is a load capacitance. I'm going to connect it to the output node. Selecting the capacitor, placing at the output node. I'm going to connect it to ground. I'm just increasing the. I will give here capacitance value 0.0 or okay, some 0.1 picofarad. I'm going to connect it. Some load capacity connecting to the circuit. For run the simulation, you see here, I'm getting somewhat a perfect square wave. That glitch is now gone. Correct, na? Sir, can I give 10 picofarad as the output node? Why you connected 0.01 picofarad? What will happen if you increase the capacitance value of the output side? Correct, na? Let me try that also. If I change that to instead of 0.01 pico, if I change it to 0.1 picofarad for run the simulation, you are able to see the rising time is not a perfect one. It is not a perfect square wave. It is like a blunted shape of square wave is coming over there. We are studying now in theory. If you increase the load capacitance, rise time or fall time is going to keep on increasing. Yes or no? That is what happening here. It is not a perfect. Suddenly it is not shooting up. It is taking some time to charge and discharge. Are you able to follow me on that? So if you increase the load capacitance, the rise time and fall time, definitely it will impact the circuit. Are you able to follow me on that? Sir, can I increase furthermore? What will happen? You let me know if I will change. Instead of 0.1 picofarad, I will change it to, let me change it to 1 picofarad now. You see what happened now? What happened now? Same circuit only. I did not change the circuit. I just increased the load capacitance. Correct, na? What happened right now? Can anyone justify? Complete deformation. It is not at all working properly. Why? See, huh? The capacitance size is very big. Correct, na? But the duration you are giving it to charge and discharge is very less. Before it completely charges to 1 voltage, the next cycle half time comes, it is discharged. Correct, na? So you are not giving sufficient time to charge or not sufficient time to discharge also. Correct, na? So if you are increasing the load capacitance, definitely you cannot work at a high speed. You have to reduce the speed. Sir, my load capacitance is fixed. Then what should I do? You have to decrease the speed of the clock cycle. Previously, my clock speed is 100 nanoseconds time period. You reduce it to slow clock cycle. You give sufficient time to charge, sufficient time to discharge. Then it will work properly. Are you able to follow me? Sir, my speed also fixed. 100 megahertz only. Load capacitance also fixed. But how you can make the circuit to work on now? You understand my question? Yes or no? First, what I did, I increased the load capacitance. The circuit is not working properly. I want to make the working properly. Either reduce the clock's input speed. But then the second option, what I give, don't change the load capacitance. That let it be 1 picofarad. Don't change the input speed also. But I want that circuit to work at same speed, same load. How will you make that circuit to work on? That is the problem of designers right now. Correct, na? They will give some specification. You have to design and give. That is your job. Now I am giving one task for you. Design an inverter which can work at 1 picofarad, which can act at 100 megahertz, 10 nanoseconds the period of the clock cycle. Correct, na? These things are fixed. Design an inverter. You know the circuit diagram of the inverter also. What are the changes you can make to the circuit now? Such a way that you can make that circuit to work at 100 megahertz with this particular load. You are a VLSI design engineer if you study this subject. Correct only, no? Yes or no? What is the purpose of studying this subject? What are the changes you will make to the circuit to make that circuit to work at this speed and with this load? If you have studied the subject, you should be able to answer to this. In the same class, I gave the example. If you increase the width of the transistor, what will happen? Using the drain current equation, ID is equivalent to mu n C of W by L VGS minus VT the whole square. Correct, na? In this circuit, voltage I am not changing anything. Correct, na? And if you increase the width of the transistor, ID is directly proportional to width of the transistor. Correct, na? If you keep on increasing the width of the transistor, the current carrying capacity of that particular circuit will keep on increasing. ID is directly proportional to width. If you increase the width, current will increase. If your current is more, frequency of operation will also be more. Are you able to follow me? You see, same transistor, instead of sending 10 microamperes of current, if it sends 100 microamperes of current, the charging will be very fast. Correct, no? That's what I said. If width of the transistor increase, if you are increasing, more current will flow through the transistor. So immediately it can charge and discharge the capacitance. Are able to find. So how can you rectify the problem? Just increase the size of the transistors so it can work at a huge load. It can work at a faster speed also. Correct or not? But whether it is good or bad? Bad. Why? The size of the transistors are increasing. It is consuming more power. Only advantage is working at a high speed. Correct or not? It is working at high speed with a heavy load. But all the things you have to sacrifice. That is the problem of VLSI design engineer. If you want to increase on one thing, there will be a drawback on other two things. Trade-off. If you want to buy something, you have to pay something. If you want to achieve something, you have to sacrifice something. If you want to achieve the speed, increase the size. That's how it's a trade-off over there. Somewhere you have to balance your circuit design. It works at all the needs. Am I clear or not? Okay. So this is what VTC, transient analysis of inverter. And I will just stop with the last one command. What is that now? I defined here it as something called as V in and something as V out. I named that wires as a name, labeling for the wires. Correct, na? How can I do that? You go here, some A option is there, na? Click here, you will get an option for example, I will give Maran. I want to define this wire as input, na? Select here, input. Okay. If you want to place it here, you can place it anywhere. For example, I will place it for roughly, I will give it here. You can place it anywhere. I defined that wire as now input with the name of Maran. Here, similarly, only I did for V in and V out. Here I defined it as input port. Here I defined it as output port. Correct, na? So that it is easy for you. Otherwise, it will just number it as node 1, node 002, like that it will mark on. To avoid that, to have some clarity on your circuit, you can do these things. Sir, I want to try for an AND gate, NOR gate. Now I have only 2 transistors. Based upon an AND gate and NOR gate, connected to the circuit. Instead of 1 input, you have to take 2 inputs, give the clock signals accordingly, and verify your functionality. Am I clear or not? I have given the demo not more than 1 hour I took, I hope so. Not more than that. 9:15 to 9:30 only I started. 1 hour 15 minutes I took. Correct or not? All the 3 experiments I was able to complete. You should also be able to complete. Okay? Do it on. I will close the window, go for break, then we will have the